Okay, shall we start this plenary session? And I'm Paul Valdez, and I am delighted to be able to introduce our plenary speaker for today, Pascale Braconnot. I've known her now for many years. She is one of the leading climate modelers and leading paleoclimate modelers, but works in all time domains from the past to the future, and is very, very active in many aspects of the whole sort of climate modeling arena. She was awarded the Milankovitch Medal in 2009, Legion d'Honneur in 2012, and elected to the Académie Européenne in 2015. So has had many awards and honors. She has also led the PMIP project, the Paleoclimate Model into Comparison project, or co-led it for many years. And it's through that project in particular that I guess we've particularly worked together. So today, Pascale is going to be talking about the role of paleoclimate model, and particularly the thoughts of the role of paleoclimate model data comparisons in assessing climate projection levels of confidence. And so with that, I will hand over to Pascale. Thank you.
Okay, so thank you, Paul, for this introduction. So I will share my screen. So this is, sorry, I'm not at the beginning of the presentation. I would like to thank the organizers for letting me the opportunity to exchange a few thoughts. Of course, I will even if I speak about model data comparison, I will be biased to the modeling side of it. And as with a smile, I invite you to look at this very nice picture here, because it's the faces of our models we use in PMIP, and they're looking at you very anxiously to know if they have the right skill to do what we ask them to do, in particular when considering future climate projections. So we cannot just tell them they are good or bad. The story is much complex than that. And that's why I put levels of confidence in the title somehow. I'm biased to the modeling, and we all know we are running models for lots of developing and running models for lots of different things to understand the mechanisms of climate, different timescales in there. Also identify how the climate is working and response to external factors. That's the famous forcing. We also have academic simulations to test hypotheses, and today with a view on exploring the future we discuss. But I would like to emphasize that we need all of these things to be clear about what we are doing for the future and make sure we ground our information on the science. With time, the models have evolved. I'm also biased towards the global general circulation models. But they have evolved very fast from atmosphere alone and atmosphere with slab ocean model 30 years ago to test the climate system, to now models that have different levels of complexity, with some of them including all the coupling between vegetation, ocean, biochemistry, and so on. So the questions are becoming more and more complex. It's more and more difficult to disentangle all the different effects. And I would like to say that in practice, it's not clear we are reducing uncertainties. We are certainly increasing uncertainties because there are more to learn, but we have increased our knowledge, and that's why we are able to discuss these uncertainties now, and that's part of also the story behind the Paleoclimate Modeling Intercomparison project. So this project was launched in 1991. You have a figure of the first people attending the first PMIP meeting or the PMIP, where PMIP was decided, sorry. And we celebrated PMIP's 30th anniversary last December. It was a great period. And we also had the opportunity to have this nice special issue of the Pages magazine, and I would like to thank Pages for that. So since the beginning, PMIP is about understand and evaluate, and those two words need to be tied together, as I told before. And the result of PMIP have been very important for, and a resource for the IPCC reports when we look at those reports. Of course, Paleo brings the model in a different context from the one they are developed, that is the modern one that is very short period of time. And we address questions that are very relevant for the future climate, climate sensitivity, hydrological cycle, climate variability, and also the linkages between climate changes and environmental changes, even though it's in gray there, because I think we should do much more about it. Okay, so PMIP is also part of a broad ensemble with some of our key periods, because we need to gather people around key periods so that we have enough groups running similar simulations and enough people also looking at similar periods between model and data. So since the beginning, we had the Middle Ocean and the last glacial maximum, and then now we also have last millennium, last interglacial, and mid-Pliocene, that are part of the broader ensemble where people join effort at the international level with CMIP to characterize the response to different forcing, the model bias, if they have an impact of the model response, and what's going on for variability and the future climates, what we can tell. PMIP is not only this period, and we have also lots of different time scales, like a deep time or the prompt challenge now on deglaciations, and looking also at rapid events. But it's all about simulations, so it's not directly the models, and climate reconstructions from different climate archives, and there is a lot to do with that, and model data comparison with different methodologies. Okay, so when PMIP was launched, it's very nice to see this early time. You had people really gathering from different perspectives, but they all wanted to know more about climate sensitivity and the response of the climate system to external perturbations or forcings. And because of this, the last glacial maximum was chosen as a key period for PMIP. And when we run this simulation, unfortunately, everything is still not fully interactive in the models. And we have to impose reconstruction of the ice sheets that comes from a combination of data and modeling. From ice cores, we can get the atmospheric compositions. And we also have to think about the Earth's orbit, but for this exact period in the last glacial maximum is not that important compared to today. And then that's what happens, is that we all have to work in hands, and little by little we understand better the system and feedbacks. And the ice sheet, for example, is a big topic for the last glacial maximum, because there are still lots of uncertainties on how what's the exact ice sheet at that time. And you can see on this figure that depending on the reconstruction we're using, the domes, the position of the domes in the northern hemisphere on the Laurentine ice sheet, or the exact extent of the ice sheet varies from one reconstruction to the other. And key question also for the southern hemisphere on the relative size of the east and west Antarctica. And all of this, of course, has impact on the magnitude and the cooling at the regional scale, and also the climate at regional scale. Okay, so a few words about climate sensitivity. The definition is a modeling one somehow, where normally it's the temperature you get with a doubling of CO2. Of course, in the real world, it's not only CO2 forcing climate, so the definition must be enlarged to the different forcing and the temperature response to them. And this forcing is seen as a perturbation of the Earth's energetics. What happens when you have a forcing? Because of the way the ocean and land react, and in particular for the evaporation, that is very different between the two, you have a land-sea contrast. And this land-sea contrast is seen in all the different climates with almost the same values, I would say, which is for us an opportunity to use the paleoclimate records of the land and ocean that are really independent in practice to see if models are able to reproduce this first order pattern of the climate response. And this has been done since the beginning in PMIP, and I have an iconic diagram here with the change in temperature of the ocean and the land with all the PMIP simulations. Each dot is the result from a particular model, with the red one for PMIP4, and you can see they are slightly colder somehow. It's due to ice sheet and model complexity to make it short. And then you can see that from the reconstruction, then for a long time, we have the bar line and marker reconstruction for it. You can check what the model are doing and if they fit with the data, which is the case here. And then I have a strange figure on the right, and it can be misleading just looking at this like this, because you see that with a new reconstruction from Theater or the one we have from GLOMAP or Tierney, we have very different vision of the things. And part of it is just due to the fact that it's more data points. So that's the model are sample where we have data. And this is why we have now more data, region we've called the climate. That's why there is a shift. And some of the models here that fits with the data we learned at the same as the one on the other figure. But I would like also to raise the point that we have still lots of questions, like for example, for the ocean here, you see those two reconstructions. Behind that, you have what type of record you consider in those reconstructions, how you do it, and there are lots of new products now also with proxy assimilation, so that's great, but raises questions about the exact reconstruction we have. And then we still have to understand what the different proxy tells us and how we can sample the data as close as possible as the reconstructions, and also certainly better use what we can do now with proxy modeling, like isotope modeling, or also biochemical modeling, and so on, to really understand how we best compare the models with the different reconstruction and improve the assessment of this Nancy contrast. What is very interesting now too is that we can go further by looking at the similar things with different periods of time. And then the story becomes a little bit more complex, because you can see that it's not a straight line when you consider all the present world climate, the present day, the future climate projection, and Eocene climate optimum. And then we can address this question by combining all this information from different time scales, is that some of the models now have higher sensitivity than before, and we know that the paleoclimate reconstruction tells us that it might be too big. So what do we do with that for the models? We know now that there is a dependence with the mean climate state. It was discussed quite a while for the last glacial maximum for the feedback for clouds, for example, but there are also other feedbacks from water vapor that we need to consider. So what is this dependence, and how can we assess that, and also help to assess this from different models? And also there's a pattern effect that we need to better understand depending on the forcing. And there's lots of examples in the past where we can go on. So I really encourage to continue this exploration with the different climates. And we can do it now with all what has been produced. Another point on climate sensitivity that is discussed is that we have this polar amplification, is that the changes are larger in the world, the warming, for example, for future climate. It has to do with, of course, the fact that we have ice, snow, and so on, and also the characteristics of the boundary layer in the atmosphere and the clouds. What happens when we look at different types of reconstructions is that in most models you have a relationship between the temperature change and the change in the temperature change in Arctic here for Middle Ocean, for example, and change in sea ice. And there seems to be that models have too warm, so it may be because there is too much sea ice, or because we are too cold. And for the Pliocene also, lots of things have been done. You can see also that it's cooler than what is reproduced when you will look at the model, and there is also another estimation of this polar amplification. So all this can be discussed. And what is emerging also, so that the paleo can provide better constraint, is that now we understand better when we have similar processes between what is going on in past climate, like for example, for the last integration on this figure, and the change in CO2, and in summer, it's really the same kind of feedbacks and mechanisms, so that we can use now better the different reconstruction and what we know from model data agreement for CIs here, for example, on the figure, to provide additional information on future climate simulation and what would be the best estimates on the timing, for example, of ice melting in the north or the magnitude of warming and the different feedbacks. Okay, so move to another question now. Similarly, when you look at what happens at the early time in PEMI, people have discussed, they wanted to have periods where we could really discuss the hydrological cycle. And then the Middle Ocean appears as a period to do it, where the changes compared to present day comes from astronomy and the Earth's orbit. And because of that, we have a different latitude and seasonal distribution of insolation at the top of the atmosphere, and it drives a stronger monsoon. There's lots of things that have been looked at for this climate about hydrology. A key one has been the African monsoon. That's what I illustrate here. For a long time from reconstruction, we know that we had vegetation and more humid conditions in the Sahara-Sahel regions. From the data, we can estimate as a function of latitude here what is the amount of water you need to go from desert situation to a steppe situation here during mid-Holocene. When you look at all these models for PEMI1 and the change in precipitation, you see that they are going in the right direction. The monsoon is increased, it's nice, it's a range of responses, but then it's not enough to reproduce what is observed in the Sahel-Sahara region. So where are we now with this, what I call the African nightmare, at least for me? You look at the PEMI4 simulation here, and you see that there's improvement, and in particular, the response between all the modeling is more consistent between 8 degrees north and 16 degrees north, but it's still not enough for most of the model for the water in the Sahel-Sahara region. I have to say that some models with interactive vegetation or a few things are now able to get much closer and even very close to what is observed. But where are we? We know about model deficiencies, and we know that part of it comes from the atmospheric physics and the coupling with the land surface. But there are lots of other factors to consider, and I took this nice picture from that I had 2020, because we also need to investigate the other factors with dust, lakes, and so on. And what is missing in the picture now is the balance between all these feedbacks and what would be the best, what is the best balance, and are we able to capture it? I have to say that it's not a direct analog for future conditions. It's a way to look at how we reproduce the seasonal cycle and seasonality, measure feedbacks that will be active at any time, and also to detect non-linearities and regional pressure that are important when we discuss future conditions. Okay, so I will not tell a lot about the land surface today, except that we are dealing with a very complex system, and it's more and more complex in the different models. It's not only vegetation, but it's more complex, but and there are lots of choices, and it becomes more and more difficult to really compare the response of different models, because they do not represent exactly the same thing as it is for the different proxy reports. There are lots of subtleties in what you can get from these. So we need to dig into it to go one step further. We have also the fact that we have land use when we want to test our model for the natural vegetation for present day. And it's also an issue because it provides some difficulties for the reference periods. So the best one could be to go directly to test this natural vegetation with the past reconstructions, and you see that we might have also some concern then with the availability of data. So we have to refine the strategies, And I would like to stress that it's very important topics because it's where we combine energy, water, and carbon to really link the climate and environment. Okay, so new things that have been done too, and I'm using the result for Peter Hopcroft here, because there is a way now, and people, we would like to better introduce what we know from these past reconstructions and model data comparison to improve our models. And that's why Peter has tried to do it, and I hope we'll see more of this in the coming years, that the feedbacks from the paleo can be including in the tuning of the models, and use that for the tuning of convection schemes. And then it's possibilities to use a paired parameter ensemble to test what the effect of different parameters in the model, use emulators to mimic what these parameters are doing, and then apply the method where you choose your best parameter. And you see that indeed, when you look at the top figure, the bottom one has more precipitation because it matches something that is relevant for present day and for the Holocene. Okay, so another topic, and it's one I'm very interested personally at the moment. It's about variability, and here variability means interannual to millennium variability. And an underlying questions too, that is a very difficult part in there, is there a linkages or mutual interactions between the change in mean state and change in variability or not? Or is variability just chaotic? And then we will have lots of difficulties to really grab what can happen in the future. I used this figure from the Pages magazine, and it's a way to test variability changing depending on climate, looking at cold climate and warmer climate with 1% CO2. And then you see that you have regions where you have increased variability for temperature and precipitation, or decrease, sorry. Someone it's the same region or it's not the same region, but there seems to be a reverse situation between what you get in a cold and warm climate. So lots of things to investigate, and the PEMI variability group is very active in that, and it's connected also to what's going on in Pages. We also are going now to look at variability with this kind of indicators of standard deviation or so on, but also go to look at particular events. So lots of things in front of us. And then I also think we need to look a little bit more at detection attribution methodologies. This has been used quite a lot for the last millennium to know if we can detect the response to change in insolation or change in volcanisms and so on. And it has been extended to for the millennium to the possibility to detect at regional scale. So this is very important when the signal is detected here in the different regions, that's hydro 2K regions. It means something is there. One is above 0, that means there's a detection, and above 1, that is consistent results. And then you see that it depends on period and region. The topics for me here is not to discuss in detail these results, you will see in the different sessions, but to say that it provides fingerprints of climate response to forcing, detects signal to noise, and then it can be enlarged now to the different periods we have. And it can also provide objective measurement of model data agreement, and it's another metrics in our basket of metrics. Okay, so when we ask people what they're doing for looking at variability, of course, most of the time I'm sorry, Freeman a winner, and I'm also very interested with that. And it's about 10 years now that we are trying to bring together data people with a very high resolution records and climate modelers looking at interannual to decadal variability. It started with the Middle Holocene, of course, because it was what we had, but now we have several simulation, transient simulation of the Holocene. So it's just an example with 4 of them. And then the reconstruction from different coralline shells with time. And it's very nice because you have different places in the Pacific Ocean. So we can look at what is going on, not only in one, but several of them. One difficulty here is, of course, from the data, it's not simple to reconstruct. And from the modeling, we are not looking at the same thing as the data. They are short-lived species. So the way to do it is to sample small pieces of time in windows of 1,000 years, for example, here, to know what you get in the different simulation. And you can see that we get quite a large distribution, and it's just reflecting the fact that answer variability, this variability in the tropics is very variable, I would say, with periods with high events and low events and so on. So it's chaotic. And then we can compare to see if the data fits with what the model are doing or the rivers. And what you can see when doing that is that indeed there is a similar trend with time between model and data, even though, for example, we know it for a long time in the Middle Pacific, the model underestimates the response, even though some seems to be in better document than others. So I invite you to look at the Carrietan paper for that, for the details. And then it's very tempting because you have these records all over the place to tell, oh, but then we can know if with time we have more events that were in the Middle Pacific, that is called Central Pacific events, or something extending to the coast that are called East Pacific events, because the data certainly can tell something about it, and that's true. And there are lots of questions also about it, that the famous phases of ENSO for present day, and you can characterize them for typical pattern and moving from between this pattern for E flavor and C flavor for East Pacific or Central Pacific. So we have done that for the Holocene, but then depending on the indicators you're looking at with the same model, you can have reverse tendencies between this E and C flavor, one telling you that is increasing with time, whereas the other tells you is decreasing with time. So clearly there are artifacts there. We should have the same answer with time. And thanks to this analysis, we can understand better why we have diverse response between different publications. So I invite you to listen to Ismael de Carlo tomorrow about this story. Okay, so we are trying also to go one step further.
Pascal, just a warning that time's almost up.
Okay, so I've only 2 slides. Just one step further, and we started this thinking about it from model simulations. We've run, and in particular, we found that in some region, looking at monsoon, you have a decrease in monsoon precipitation, but increase in variability, whereas in average it's the contrary. And what's nice is that we can now try to do it using the speleothem records to help us to know if we can find such relationship in different regions. And it's what you can see that's the case from the speleothem records in these monsoon regions with different shape and trends between variability and change in mean state. And then you can see what you can have from different models. And for example, for Indian monsoon, it's quite robust what we have and with the observations. And then in the other region, it can be more complex. So we are pushing a little bit far what we can do from model and data, but we can go even further by combining now what we have over land and over the ocean. I hope to see much more on that with error bars and all the scientific discussion behind in the coming years. Okay, so it's very demanding for everybody and for data people and for these reconstructions and how we discuss them. It's an example from a project, but just to say that we have to put together all the stories, and it's lots of work, and we need absolutely to continue on that. Lots of work for everybody, I would say. And then we have to do it by considering all these uncertainties. So I like the way Ruja Ivanovic presents these uncertainties with what she called penny pentagram. And then I would just tell one thing here is that to come back to my first slide, we have to take care of what I call mission impossible expectation from the model results. because it's still very challenging to be right for present day and for climate change at the right location and for the right reasons. So that's why we have different levels in the thinking, and we need to combine these different levels to better inform future climate projections. And this can only be done by continuing to be grounded in international communities, of course, within PMIT, but also all what's going on with pages and WCRP, and that's my last slide. So thank you.
Okay, thank you very much. I've got the privilege of being able to clap, and I'm the only person I think who can. The time is pressing now, so there's one question that's come up. You've been very heavily involved in IPCC over the years. What do you think is the place of paleo in IPCC? Do you think that the recent report where it was integrated, was that good? How will that look in the future? Okay, so the paleo has always been there as a key thing in the IPCC reports in the beginning, and depending on time, you have the paleo dispersed everywhere, or you have the paleo in the paleo chapter and in a few others. So clearly the paleo target is important because it brings this long-term view in the system and all what has been, and we can tell a lot about what the model are doing and so on. And this time you can see that the author have done a very, very nice job, and paleo is there, and it's there also with a few points in the summary for policymaker, which is nice, and also in the technical summary. My regrets, because I have some, is that I really would like to see more figures with past, present, and future all together. And I really think we have to work towards this goal. That means that the science needs to be worked so that this is possible, right? It's not only and we also all work in silos, so we have to go further. And my other regrets is that there is not enough paleo in this present, at least for group 1, in the regional chapter. And the same, there's a lot of information we have at regional scale. We know a lot about this integration. Regional scale is a multi-factor approach. And then all what we have with model and data or model whatsoever have much more to say than is in the report. So I think it's a way we present and we think. It's not doing differently. It's just a way to really capture where we are and be able to not only say, that's what I said at the beginning, is good or bad, but how we can use what we understand from this path of this model data comparison, not necessarily to a subsample model to take the good one, but to bring something that is knowledge and information in the way we present also future climate possibilities. Thank you. I've just got, I'm conscious of time, but there was one comment, well, it's really a comment from the audience, which was to do with saying that, you know, you talked about models testing hypotheses, but isn't it really that models formulate hypotheses that then can be tested, well, experimentally against the observations? And it's a sort of philosophical one almost about, you know, the role of modeling. I think that's both sides. And when we look at PMIP history, I think that's what really happened with time. We are, depending on what we have done, the question has been from the data because we wanted to understand something, or it has been from the models because suddenly we highlight a key question where it's difficult and how you can test it better compared to the reconstructions. So it's both sides. I would not say one is better than the other. Yeah. I'll do one last thing. As I say, time is basically up, but is there anything that PMIP would like specifically from the Pages community? Is there anything you can identify which Pages need to push? So it depends on people, of course. So to say there's
already a lot. When you see there are lots of talks I've seen where PNIP simulations are included in model data or whatever. So that's great. There are a lot of pages group where we have model and data. I really would like to see more integration between the two, even in pages groups. Pages is very, very nice for, it's really where we have the big resources in PNIP all those years for the reconstructions and the in-depth discussion about what we can get from the different types of data, I would say. And this is even more pressing now to make sure we have the right interpretations of this data so that we can grab the exact story that each data set can tell us and figure out how we can sample the model so that we're looking at the same stories and not pear and apples, because it happens all the time, we're not looking at the right thing. So for me, really, Pages is instrumental for that. And I would say there are lots of periods that are now in PNIP, and to have a close collaboration is very important for that. So I have no definite answers. I didn't discuss today rapid events, right? Not the ocean, even though I'm an oceanographer to start with. So there will be more and more on that, and the timing and so on. So we are moving also, even if we will keep these time slices for a long time in PNIP, because you need to bring this together. But then we see that more and more we have these dynamical views of the climate system, and even if it's possible now with these big models, we have these deglaciation challenges, and we have all these transients. So it's another way to think about the system, but also to think that maybe present day is not a reference when we do those comparisons.
Okay, thank you. I think we definitely now need to finish now. So I think it's well, coffee time for people in the European time zone. Might even be a glass of beer or wine for those in later time zones. We leave you to that, and it's my pleasure to be able to just thank you, Pascal, again for a very interesting and stimulating summary of the role of model data comparison. So thank you, Pascal.
Okay, thank you. I thank you to Pages, and I hope lots of model data.